Alright everybody, welcome back. In this video we are going to talk about information from section 7.6 of AP Calculus, finding general solutions using separation of variables. Alright, so a differential equation, y prime, which is a function of both x and y, is separable if f can be expressed as the product, not some product, the product of a function of x and a function of y. So any differential equation that we can split into some function of x times some function of y is one that we can use separation. So that's when we can use the technique we're going to talk about today. There are times where you might see something like dy dx equals function of y, in which case we're going to need to separate, and that's what this little Thomas tip is about here. Kind of, to help you figure out when you need to use separation and when you don't. If you look at an equation and the variable that appears in the numerator of your differential appears on the right-hand side of the equation, then you're going to need to use separation of variables in order to integrate. Alright, so how does it work? Separation of variables, a how-to, and we'll go through this how-to written specifically for a differential equation of the form dy dx. First things first, notice that the variable that's in the numerator of our differential here in part A is on the right-hand side of the equation. Okay, so first step, using appropriate algebraic steps, separate all the factors containing y and dy to one side of the equation and all the factors containing x and dx to the other side. So in order to do that in this problem, and we always want our dy and our dx to be in the numerator of their particular side, so we want to bring all the y's over to the left-hand side and all the x's and dx's over to the right. So in order to do that algebraically, I need to multiply both sides by y here, and also multiply both sides by dx, and that gives us that y dy is equal to x squared dx. Okay? Now from here, we can just go ahead and integrate both sides of this equation. We're going to take the integral of y dy on the left-hand side and the integral of x squared dx on the right-hand side. The integral of y dy is 1/2 y squared plus a constant, and the integral of x squared is 1/3 x cubed plus a different constant. And in reality now all I need to do is solve this equation for y. But I'll tell you, before we go any further, this step that I just wrote down, I will never ever write this step again. We will always, in separation of variables, end up with a constant of integration on the left and a different constant of integration on the right, and I will always go directly to just combining those two constants of integration on the right-hand side of the equation. So I would jump directly to this step, 1/2 y squared equals 1/3 x cubed plus a constant. And now from here, my task is to solve for y. I'm going to multiply both sides by 2. And when I multiply this constant by 2, I get another constant. And by the way, I could absolutely, and I'll tell you this, I could subscript all these constants. This is a new third constant, and when I multiply both sides by 2 and I multiply this by 2, it gives me yet another different constant. But I tend to just, use c all the time and kind of keep track in my mind of whether or not, two c's are equivalent to one another. And now to get y by itself, I take the square root of both sides of the equation. And when I take the square root of the right-hand side, everything is inside of the radical. And so that would be our answer. Like I said, in general, I'm not going to subscript my c's, so I would end up here with just y equals plus or minus the square root of 2/3 x cubed plus c instead of a c4 there. And that's how we do separation of variables. Let's go ahead and we'll look at, I kind of shunned going through my steps here, integrate both sides of the equation using an appropriate previously learned technique. That's what we did here. In this case, I could just use antiderivatives. Sometimes I might need to use substitution. Sometimes, for those of you who are in BC, I might need to use another technique that we've learned in BC that, AB students haven't learned. And then I'm going to solve for y. And I say here in my outline, in all honesty, this is usually the most difficult step. I mean, the first two steps, separating things algebraically and then integrating, are pretty much the same from problem to problem. But this third step, solving for y, there's a little bit of difference in how we solve for all of these. Some of them can get a little bit complicated. And some of them are pretty straightforward. I feel like this one was pretty straightforward. We'll see some complicated ones pretty soon, though. All right, example 1b, dy dx equals cosine of x times the quantity y squared. First thing I'm going to do is I'm going to separate my variables. So my dy and my y's are all on the left-hand side, and my dx and my x's are all on the right-hand side. I do that by multiplying both sides by dx and dividing both sides by y squared. And so I end up with dy over y squared is equal to cosine of x dx. And again, I could use separation because this is the product. This is, some f of x times some other function g of y. So since it's the product of a function of x and a function of y, I can separate. All right, and now I want to integrate both sides of the equation. The antiderivative of dy over y squared, that's the integral of y to the negative 2 dy, so I can just use the power rule. It's going to be y to the negative 1 over negative 1, or I can jump directly to negative 1 over y. And the integral of the right-hand side is going to be sine of x plus c. Okay, so separating, integrating, not terribly difficult in this problem so far. Now we need to solve this for y, so I'm going to multiply both sides by a negative. Sine of x times a negative 1 is negative sine of x. A constant times negative 1 is yet another different constant. And then in order to get y here, I'm going to reciprocate the problem. So I'm going to flip this side, 1 over y becomes y, and I'm going to reciprocate this side, which means I need to take that whole side of the equation and put it as the denominator of a fraction under 1. And there is my general solution for dy dx equals quantity cosine of x times quantity y squared. All right, let's keep going. We've got a bunch more examples here. Part C, dy dx equals x squared y. So first things first, I'm going to separate. So we've got dy over y is equal to x squared dx. And then I'm going to go ahead and take the integral of both sides. The integral of dy over y is natural log of the absolute value of y. And the integral of x squared is 1/3 x cubed plus our constant. And now in order to solve for y, we want to take both sides of this equation and take e to that power in order to get rid of the natural logarithm so that we can solve for y. So we're going to take this side of the equation and raise it e to that power. We're going to do the same thing on this side of the equation. Here's where the algebra gets a little fun for us. Left-hand side is not too bad. E to the natural log of the absolute value of y is just absolute value of y. On the right-hand side, we need to think a little bit here. When I have e raised to 1/3 x cubed plus c, that means that this side of the equation is equal to, using exponent properties, this is e to the 1/3 x cubed times e to the c. Make sure you stop and think about that for a second, that if I multiply these two together, since they have the same base, we just add the exponents, and that takes us back to what we had in the previous line. All right, now, the other thing we should recognize is that when we take e and raise it to a constant power, the result is just another different constant. And so this is equal to absolute value of y equals, and now I'm going to change this to a different constant and bring it out in front, and this becomes that the absolute value of y equals ce to the 1/3 x cubed. Now, again, I'm going to be honest with you. Usually at this point, when I take something like this and raise e to an expression plus constant to a power, I just jump directly down to this spot here. Because I've done enough of these, I don't need to go through the algebraic steps to prove to myself that that's just a different constant. And then to solve for y, since we're taking the absolute value of y, that means y could be equal to plus or minus what I've got on the right-hand side. And you'll hear me say this a bunch when we're solving for specific. This is an okay place to stop when we're solving for a general equation using separation. But the other thing, too, is this constant c, we don't really know if it's positive or negative. And so to say plus or minus this constant c, I can just change it to some other different constant. You know, if it's positive, then it just stays the same constant. If it's negative, then I change it to the opposite constant. And I can, either way, I can express this as y equals ce to the 1/3 x cubed. So that's where I'm going to stop. Are you okay here? Yeah. I would really accept either of those in this problem. All right, do I have time for one more? Ooh, it's going to be close. Let's go ahead. Now, in order to do this one, we've got a plus sign here. So the first thing we need to do is we need to sort this into a product of two functions. And the way we do that, we can just factor a 4x out of both terms. And now the right-hand side of my equation is a product of a function of x and a function of y. And so from there I can separate dy over y plus 3 is equal to 4x dx. I integrate both sides. And when I do that, I get natural log of the absolute value of y plus 3 is equal to 2x squared plus a constant. I raise both sides e to that power. The left-hand side simplifies to absolute value of y plus 3. The right-hand side to ce to the 2x squared. Again, new constant. And then y plus 3 is going to be equal to plus or minus ce to the 2x squared. And then I can subtract 3 from both sides, and I get y equals negative 3 plus or minus ce to the 2x squared. This would be an okay answer. Again, since we don't know whether c is positive or negative, I can absorb that plus or minus into it, and this could be written as this as well. And then this sign, you know, if it just determines whether this is going to be positive or negative. All right, we're going to stop there. We're going to come back in a second video and do a few more of these problems. 3 that those of you who are in AB will be able to do, and then a 4th just for the BC folks. But anyway, that takes us to the end of this video. We'll see you next time. Have a great day, everybody. Bye-bye.